So we are solving the ninth problem in this series. So the problem is 3.9 and the problem is stating a thin wire ring of radius r carries a charge q. Find the magnitude of the electric field strength on the axis of the ring as a function of distance L from its center. Investigate the obtained function and find the maximum strength, magnitude and the corresponding distance L. Draw the approximate plot of the function E as a function of L. So we have a big problem to deal with. So in order to start, we are considering that a ring is placed like this, and we are providing a positive charge to this ring, which is a charge q, which is uniformly spread over the entire ring. The next that we say is that the charge q is spread on it, and we are dealing with the radius as r. Now over here at a distance L from the center of the ring, we need to evaluate the value of electric field strength. So if we select a elemental charge over here, which is a small elemental charge which we consider as dq, then this dq is going to create an electric field at this point, which will be in the outward direction like this. So over here, which we are referring as DE, a small electric field DE, and this angle is theta. So we can consider this component as DE cos theta component. So all the electric field contribution of the sin theta component will cancel each other, which we are not drawing here, because the other component, that is DE sin theta, will be cancelled by a charge element here. So we are not drawing DE sin theta. So we consider that on the axis of the ring, we say electric field on the axis of the ring is equal to contribution due to DE cos theta integration. So all the DE cos theta element will contribute to make the total electric field strength on the axis of the ring. So now in order to calculate this value, we have this distance as small r, and this is at a distance L from the center of the ring. So this distance can be written as L square plus R square square root. So therefore electric field on the axis of the ring can be written as integration of k dq by distance. So this distance is equal to L square plus R square, and followed by this we have a cos theta term. So cos theta can be written as L upon root over L square plus R square. Now for any elemental charge dq on this ring, the value of cos theta is remaining unchanged. So therefore this integration is not as tough as it seems. So we can simply write it as kl upon L square plus R square to the power 3 by 2, and then we have integration dq. So on integrating all the charges dq, we obtain electric field on the axis of the ring can be written as L upon 4 pi epsilon naught L square plus R square to the power 3 by 2, and this is total charge q. So we can also write it as kql upon L square plus R square to the power 3 by 2. So this is the first aspect for the problem which we are solving. So this is in terms of 1 by 4 pi epsilon naught, and this is the second aspect for the problem which we are solving. Now the second part is asking us to approximate the result when L is greater than R. So for L greater than R, we can simply say that this entire system of charge will behave like a point charge. but we need to say this mathematically as well. So for L greater than R, we can say E on the axis of the ring can be written as KQL, and over here if we take L square common, then we can take it as 1 plus R square by L square to the power 3 by 2, which on solving we have KQ by L cube 1 plus R square by L square power 3 by 2, and we have a term of L up there. So since L is huge, so we can say E on the axis of the ring will then approximate as KQ by L square. That is, we can say that it will behave like a point charge. So at a great distance, the entire ring of charge can be considered as a point charge. Now the next part is to calculate the maximum value of E. So we again approach the problem for calculation of magnitude of E on the axis of the ring to be maximum. So we approach the problem from the formulation that we derived, that E on the axis of the ring is equals KQL upon x square plus R square to the power 3 by 2 L square plus R square to the power 3 by 2. So using this we are deriving the condition for maxima. So for maxima we can say dE by dL must be equal to 0. So this will give us the maximum condition. So we say hence dE by dL must be 0, and if we differentiate this term, then we say since we have the term of L on both numerator and denominator, so we are first of all using denominator squared. Now keeping denominator constant, we are differentiating the numerator, and then subtracted by keeping numerator constant, we are differentiating the denominator. Keeping numerator constant, we are differentiating the denominator, and then we will equate this value to 0. So over here we obtain L square plus R square to the power 3 by 2 KQ minus KQL 3 by 2 L square plus R square power half, and then L square is differentiated as 2L, and over here on equating we obtain L equals plus minus R by root 2. That is, we can say on the either side of the ring at a distance R by root 2, the magnitude of electric field strength will be maximum. So the next part is to find the maximum value of field. So E maximum magnitude is at this point which is equal to R by root 2. So we can write it as KQL upon L square plus R square to the power 3 by 2, and this can be written as KQ R by root 2 R by root 2 square plus R square to the power 3 by 2, and on solving we obtain this value as Q upon 6 root 3 pi epsilon naught R square. So this is the maximum value of electric field strength, and it is at the point R by root 2. Now the last part of the problem is to draw the graphical variation of this field. So if we are plotting the value of magnitude of E with distance L, so we can consider this graph that if this is the magnitude of E, then we can say that this is the magnitude of E and this one is L. So we obtain a graph like this at this value, the value is equal to 0, as the equation is KQL. So if L equals 0, the value of field will be 0. At a distance of r by root 2, it will attain a maximum value, and then again at a greater distance it will behave like a point charge and the value will nullify itself. A similar graph can be obtained on this side. So we will obtain a graph like this. So this is the maximum point, this is the point of maxima, that is r by root 2. So we obtained the two values plus minus because of this reason, that the value of electric field strength will be maximum on either side of the ring, and at a greater distance it will start behaving like a point charge, and this is the maximum value of the field, which we have calculated as q upon 6 root 3 pi epsilon naught r square. So this is how we solve this wonderful problem 3.9 in this series.